Good day and welcome to my YouTube channel. I am Arthur Francis Deba. Please, you have to do some justice by subscribing and press the like button. In our last class, we were talking about organic chemistry. We've done the introductory aspect of alkanes and all it entails. I gave us the general molecular formula of CnH2n plus 2. We talked about some of its reactions, combustion and substitution reactions, which we have exhibited. We will also talk about the classes of carbon, the primary, secondary, tertiary, and quaternary. And through the general molecular formula, we are able to determine the molecular formula of all the members of alkane, which is the methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonadecane, and so on. So today we're going to start from the isomerism of alkanes before we now move into alkenes, God willing, then into alkynes. Now, what is isomerism to begin with? Isomerism is a phenomenon where a compound having the same molecular formula but different structural arrangement. The molecular formula is the same, but the structural arrangement is different. Now, I will take a practical example. Let's take butane, which is the first member in the alkane family, or the lowest member to exhibit what? Isomerism. Let's see how that works in that case. We have butane is C4H10. Now, it means we have 4 carbon atoms and 10 hydrogen associated with it. Now we say isomerism is a process where a compound has the same molecular formula but different structural arrangement. Let's see how many structures we can get from this. Let's take the first one. 1, 2, 3. Then I have 1 here. I also have 1, 2, 3, and 4. So here, if I put my hydrogen, good. Now, remember I told us earlier that carbon is tetravalent, which means it has 4 bonds surrounding it. This carbon has 1, 2, 3, 4. This one, 1, 2, 3, 4. This one, 1, 2, 3, 4. It is important you know that. So now, if I count C4, 1 carbon, 2 carbon, 3 carbon, 4 carbon, I have 4. Let's see the hydrogen to be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this molecular formula of butane, I have my C4H10. The structure here is different. Let's look at this other side. 1, 2, 3, 4. The same 4 carbon, hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see, we also have H10. Now, what do I say again was isomerism? A phenomenon whereby a compound having the same molecular formula but different structural arrangement. The structure here is different from the structure here. That is isomerism. And there are many cases where we can have 2, 3, 4, 5 isomers. So the first guy here, which is the butane, this is C4H10 for butane, and we have this straight chain for butane. We call it N-butane. N-butane, which means normal butane. But in this being the normal butane, this now is an isobutane, an isomer of butane. So we're going to check another compound to see how many isomers we can get. So we've gotten our first one from this. Let's take the second one. Remember, in our case, our general molecular formula remains as CnH2n plus 2. So let's take hexane, for example. C6H 2 times 6, 12. 2 times 6, 12 plus 2, 14. H14. So this is our molecular formula. Let us see the isomers we can get from it. 1. I put 1 here and 1 here. Now, 1, 2, 3, 4, 5, 6. It is 6 carbon atoms. 1, 2, 3, 4, 5, 6. 6 carbon atoms. 1, 2, 3, 4, 5, 6. 6 carbon atoms. 1, 2, 3, 4, 5, 6. 6 carbon atoms. The hydrogen. Well, I will put them for the sake of those of you who may be watching our lectures for the first time, but we have masterminded a method whereby we can, with this, we just proceed. We know that hydrogen atoms are associated with each carbon atom in a manner which gives us tetravalent. So let's just put it for the sake of that. I have So in all of these cases, we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 for this. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in all the cases we have what? C6H14. So all of them still give us what we call our isomerism. By definition again I say an isomerism is a phenomenon whereby a compound have the same molecular formula. The molecular formula is 6,6H14, but different structural arrangement. Their structures all are different, but all of them have 6,6H14. So this is what a pure example of the various isomers we can capture here so far. So this one is N-hexane, normal hexane. This one is 2 methyl This is 1, 2. In carbon 2 we have 2, 2. So this is 2,2-dimethyl butane. While this is 1, 2, 3, 4. This is 2,3-dimethyl butane. So we have done the naming, how to name the various compounds in our previous class. In case you have forgotten that, you have to go back to it so that you will not be lost. So in the course of naming this one, at least it will be faster for us. So that is what it is. We just have to show isomerism before we move to alkene. Now remember, if I give you another one, let's quickly, before I move further. If you were to be having C7H16. Now, what do? The first one, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This is our normal heptane. Don't mind the hydrogens are not there, but now I want to break it down. You understand what I mean by that? Now, what do? The best way to get isomers, if you cut one of these, you put it anywhere, it has given you one isomer. You cut 2 of these, you put them anywhere, it gives you another isomer. You can even cut 3 based on the length of the chain and put them, know how to fix them. It gives you another isomer. Let's take that is N-heptane. Let's take that, I'm cutting 1. 1, 2, 3, 4, 5, 6. That one I cut off. This is where it is. This is 2-methylhexane. That's my first word, isomer. Now I want to cut 2. 1, 2, 3, 4, 5. I'm having 2. 1 here, 1 here. This is 2,3-dimethylpentane. I have another isomer. I want to cut the same 2 again. Let's take it that way. 1, 2, 3, 4, 5. That same 2, but this time I put them in the same carbon atom. I have 2,2-dimethylpentane. Then I can still break it further. I can take out 3. If I take 3, I'll be left with 4. This is 4. And I have 1 here, 1 here, and 1 here. My parent chain is 1, 2, 3, 4. Or 1, 2, 3, 4, whatever it is. So I can name this as 2, 2, 3 trimethylbutane. Because in carbon 2 I have 2, and in carbon 3 I have 1. So this becomes 2, 2, 3 trimethyl butane. All of these are isomers of what? Heptane. So the best way is you break the bond and attach it continuously. You continue to get as many compounds as possible. All of them are isoheptane, but this one is N-heptane, normal word, heptane. So these are isomers formed from what? Heptane. Alright, the business of the day. We want to deal with the alkenes, the few reactions it undergoes, and isomerism, and the rules of naming what the alkene family. So let's say that quickly. I can take this one out now. Before I do that, I'd like you to tell me the number of isomers you can get. It's an assignment. You send the answer to the comment section. I will see into it. The number of isomers. How many isomers can you get from octane, which is 8 carbon atoms? Do it and send it to me. I will confirm the number of isomers you can get there. So let's take alkenes. Now, in alkanes, we say the general molecular formula was CnH2n plus 2, and all members of the alkane family were replaced with ANE. So if I have butane, this is butane ANE, because butane. Now, in alkenes, all the members will be replaced by what? The ENE. We use it to replace them. So we start with the first member of the alkene family. We do not have that method. We have 18 as the first member. So I have 18 propene, butene, pentene, and so on and so forth. Now, how do we know how many carbon atoms and hydrogen atoms will be there? Remember, the alkenes are unsaturated hydrocarbons, which means they have double bond between their carbon atoms. So let's start. Their general molecular formula is CnH2n. This is their general molecular formula. So if we use this, let us see what do we get in 18. 18 means 2. Am I right? So now I have C2H2 times 2, 4. Propene, C3H2 times 3, 6. Butene, C4H2 times 4, 8. And 5, pentene, C5, 2 times 5, 10. Now, let us see how do we draw their structures to show that this is 18 propene, butene. We say they are unsaturated, they have double bonds between their carbon atoms. Let us move further and see that. 1, 2. Now, this is 2. I have 4 hydrogen atoms surrounding it. In our case, which are saturated, this is one bonded. But in ethene, it is double bonded. So if it is double bonded, the hydrogen will be placed this way. This becomes what? Our ethene. Now, we say carbon is tetravalent in nature. It means it is surrounded with 4 bonds. So let's say this is 1, 2, 3, 4 for this. 1, 2, 3, 4 for this. And that's how the trend goes on. That is 18. What about propene? 1, 2, 3. We put our double bond. We put 1 hydrogen, 2, 3. If you don't know, some students will now put 4, 5, 6, 7, and 8. I think this is the structure because from the knowledge of the alkenes, this is what you were supposed to get. But once you do that, you become wrong. Why? Because propene is 3 carbon atoms but 6 hydrogen, and we have 8. Now you begin to check which of them is having more than 4 bonds. This carbon has 1, 2, 3, 4, 5. So take out 1. You have 1, 2, 3, 4. This carbon is balanced. This one, 1, 2, 3, 4, 5. Take out another one. 1, 2, 3, 4. This is correct. This one is 1, 2, 3, 4. Correct. So now if you count 1, 2, 3, 4, 5, 6, our hydrogen are now complete. But if you don't have that formal knowledge, obviously you're going to put these things there and think you're good. At the end of the day, you'll be wrong. So don't forget, carbon is tetravalent. So if that is for propene, let us see for butene, which is 4. 1, 2, 3, 4. I can put my double bond here. when we get to isomerism, we'll know why it can be in the middle or here. Whenever, okay, maybe I should just explain that. Whenever the double bond is between the terminal carbon means the carbon at the end, the beginning or the end, the terminal carbon, you call it, this is butene. Normally, if it is here in the middle, the double bond is in the second carbon atom. 1, 2, yeah, 3, 4. So this becomes 2-butene. Either you call it 2-butene or but-2-ene. It depends on the one you like. So this is 2 because the double bond is in carbon 2. We call it but-2-ene or 2-butene. We are good. Now, if it is in the terminal carbon, you don't need to tell us 1-butene. 1-butene is still correct, but you don't need to tell you. If you just call it butene, we know that it is in carbon 1. Propene doesn't, all of them are terminal. You call it pentene, hexene. We know that the double bond is in carbon 1. But if it is not in carbon 1, it is in 2. It tells us 2-butene, 2-hexene. It is in carbon 3 heptene, and so on and so forth. So let's proceed. When we get into the naming process, you will know how to name that, and also the isomerism procedures that will be associated with it. Alright. So now that is for butene. Now the hydrogen atom, butene is C4H8, we've gotten our C4, the hydrogen at 8. First, I have 1, 2, 1, 2, 3, 4. This guy is correct. Now this one is 1, 2, 3. It needs 1. 4. This is 1, 2. It needs 2. This is 1. It needs 3. 1, 2, 3, 4, 5, 6, 7, 8. So this is what? Butene. It is very important you don't make those mistakes. You will see them when you start dealing with questions on your own. Let's look at pentene, which is 1, 2, 3, 4, 5. Now I put my double bond here because it is normal, the first one pentene, but we'll call it pentene normally. If it is here, it becomes 2 pentene. But then, let's see the hydrogen atom, how they're going to fit in. So I have my 1, 2 here, 3, 4. This carbon is balanced. This carbon here has 1, 2, 3. I put 1 here, 4. This one has 1, 2. I put 1 and 1 here, 4. 1, 2, 3, 4. 1, 2, 3, and 4. So this is the structural formulas for the various ethene and alkenes, which we have made mention of: ethene, propene, butene, and pentene. Okay, let us move further into reactions of alkenes. Alkenes undergo one distinct reaction that differentiates it from alkanes. That is what additional reaction. Now, when we're talking about alkanes, remember I told us about the substitution reactions, which is peculiar to alkanes. That reaction cannot be carried out by alkanes. Why? Because alkanes are saturated hydrocarbons. They have one bond, one single bond between their carbon atoms. Now, if you were asked what is the difference, a cardinal difference between alkanes and alkenes, is that alkanes undergo a substitution reaction, while alkenes undergo additional reaction. This reaction makes them unique to that end. So alkanes cannot undergo addition, and how do you call them? Alkenes cannot undergo substitution. So now we want to carry out what? The basic reaction. Of course, all of them undergo combustion reaction. So let's start with the combustion reaction of the alkene first, which is unique to both saturated and unsaturated. We used methane before to show that. Now we're going to use ethene to show the combustion reaction, which is unique to that. Then after which, we now have to go back to the addition reaction to see how can we do that and the mechanism therein. We use one mechanism to show how that can guide us to doing everything we want to deal with in terms of what additional reaction. So, alright, I said reactions of alkene first, combustion. So alkenes, we have C2H4, am I right? 1, 2, 3, 4. Good. Plus oxygen will give us our CO2 gas plus water. So let's see how then can we balance this equation. We have 4 hydrogen, we have 2 hydrogen. If I put 2 here, hydrogen is 4. Hydrogen is balanced. I have 2 carbon, I have 1 carbon. If I put 2 here, carbon is balanced. Okay, let's see if that's true. But oxygen, we have 2. And we have 4 plus 2, 6. So if I come back here, I put 3. Oxygen becomes 6. Oxygen here is 4 plus 2, 6. Hydrogen is 4, hydrogen is 4, carbon is 2. So like this, the reaction is balanced. This is combustion reaction, which is a basic reaction of all hydrocarbons. They undergo combustion. That is why they're born in what? Air. If you bring your petroleum and light it up, you see how flammable it is. So all of them undergo combustion reaction. So now, the basic reaction that differentiates the double bond and the single bond, which is the additional reaction of alkenes. Let's see that. Now, in that reaction, let's take our alkene, the first member, which is this. This is it. Now, additional reactions, we have the halogenations, which means it reacts with halogens, chlorine, bromine, iodine. We have hydrohalogenations, which is hydrogen and halogen, or hydrogen and iodine, halogen, or hydrogen and halogen. This is hydrohalogenation. We have halogenations. So any of them, hydrogenation too, reaction with hydrogen, with this. So all of this can be added with the alkene in the additional reaction. So we're going to take just maybe 1 or 2 to see how that works. Let's start with hydrogenation, which is the first one. So the first additional reaction is called hydrogenation reaction, plus hydrogen 2. Now, let me expatiate with this hydrogen. This hydrogen molecule, the ring, can still be written as this. That means that hydrogen dot and hydrogen dot. This and this come together through this bond process to give us this. And this is the same thing as this. Now, something happened. The mechanism, like I said, that's what I want to deal with. I want to show us the mechanism in the first reaction. Then you're going to use that principle to discuss or deal with the rest of them that we encounter. So let's take this. I want to replace this with this. So you'll be able to see what happens. Remember then, this, let me put it there first. So this is hydrogen molecule. Now, when an element gives out one of its electron, it becomes short of 1 electron. Whereas that sign, if it is short of an electron, it becomes positively charged. And that guy that gained the electron that came the ring become negatively charged, become having what? Excess electron, become minus. So here, this is what happens. Because in the course of this reaction, this hydrogen, the ring, will react them here to come. Okay, let me react them first. Doesn't matter, anyone. So this guy will give us this. It moves with one of its electrons. And let's say this one can still go this way. That's the mechanism. This is what happened inside that you don't see, that I want to show you today. So we have this, our hydrogen here. I now have 1 bond. This is my, let me take it this way. My hydrogen here. Now that excess that came in will make this to become negative. And this one that gave out 1 bond becomes positive. The same thing happened here. In the hydrogen, this one has given out, it becomes positive plus hydrogen negative. In physics, we're told that similar charges repel, different charges attract, which is a rule of nature. Man is never attracted to a man. Man to man will repel naturally, unless if that is being bastardized by some diabolical means. So here we go. This is it. Now, this is positive, this is negative. They are meant to come together. So this will move here. And this is negative, it will move to the positive. Don't mind me, the movement, whatever. So this is what you get. So when that happens, what do we get here? We now have, remember this hydrogen has come to the place here. So this becomes, I have one hydrogen, and now hydrogen. This hydrogen has come in here. And I have a single bond here with hydrogen here. This positive comes to the negative side and this gives us this. And down that gives us what? Ethane. So hydrogenation of alkene gives us what? An alkene. Hydrogenation of ethene gives us ethane. That is the principle. And that is natural. So at every instant, a question may come like, the hydrogenation of propane will give you what? Hydrogen of propene will give you what? A, propane, B, butane, or whatever it is they want to give to you. But you should know that it will give you what? Propane. Because it was propene, the double bond, one of it will be stripped out to give you a single bond. So whenever hydrogenation takes place, if it were a double bond, it becomes a single bond. If it were a triple bond, like we see in the future in the alkyne procedure, it becomes a double bond. You go undergo again, it gives you a single bond. Now, why do I have to show you this? It is very important. Let me show you in the next reaction which I want to carry out to see why I have to show you the mechanism and where the various hydrogens will belong. So, if I can clean this, let's take another example. The same ethene reacting with hydrohalogenation, which is HCl. So I will have this. This is my hydrogen, plus hydrogen and chlorine. Now, we want to react this. In the course of our reaction, how will you know if this chlorine, because we know in the reaction it's supposed to be either in this carbon or in this carbon. Now, how will you know that this chlorine will be in this carbon or in this carbon? You can only know that if you understand the principles of the mechanism of reaction. Otherwise, you can put it anywhere. And there will be instances where the knowledge of that will become very viable that you cannot do without it. Alright? So now let's see how it can only be here if in the course of reaction, this give out its own electron, perhaps it becomes positively charged and this is negatively coming in here. Or if this one gives out, this becomes positive and this is negative and it comes in here. This is very electronegative, more than hydrogen in the course of that. So let's see if I can take this out. Alright, if I do that again, permit me, this time let's go this way. And this will always go to the negative chlorine because it's highly electronegative, more than that of hydrogen. So now I will have here, I have this here. Okay, let me take it down, please. This is negative because it gives out its one. This is positive. And here I have hydrogen, which is positive, plus chlorine, which is negative. And I should know that chlorine will come in here because this is negative, this is positive. And this is positive, it will come down here. So if I know that, I can easily proceed by showing us that this is my hydrogen, negative, positive is going there, hydrogen will be here. And I have hydrogen, and chlorine will be here. So that is chloroethane in that case. I will carry out another reaction, but this time around I'm not going to be showing the mechanism. I only use this so that we understand what to do or what is required of us in case. So let's see what we get this time around. I'm not going to show you that, but let's see how we get in. Alright, now I want to use something like pentene. Pentene is C5 H10, if I'm not mistaken, plus this. And my C5H10 is the same thing as saying this 1, 2, 3, 4, 5. I put my double bond here. Put my hydrogen here. 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 1, 2, 3, 4 for that. Hydrogen, 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 and hydrogen. That's good. Plus HCl. I will just have my 1, 2, 3, 4, 5. The other one will be gone. Now, don't forget, this chlorine must come to either this carbon and this carbon, and never this or this. Why? Because the reaction is taking place in breaking this bond, so it can either come here to make it negative or here to be negative. So if in the course of you bringing your chlorine and you put it anywhere here, you're wrong. Just have to, you're gone. You feel it directly. So it must be this carbon or this carbon, the carbons that have the double bond. I want to show you this so that we'll be able to, so we'll be able to see how that works again in another compound. So this is it. 1, 2, 3, 4, 5. Now I have my chlorine here, I have my hydrogen here, hydrogen, hydrogen, and so on we go, just like that. So remember it was an alkene, but now it is not an alkane, and this is 2-chloro, it is in the second carbon, this is 2-chloro, 1, 2, 3, 4, 5, pentane. In that case, let's see this kind of the same reaction, but differently. So if I have my 1, 2, 3, 4, 5, I'll have my double bond here now. My hydrogen, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3,